Section 2 from Unit 2 is going to talk about early ideas about matter. So it's going to go into sort of the history of chemical thought and how chemistry became a science, which is kind of cool. So really the whole idea of chemistry starts all the way back with the Greeks. At that point, finally, societies are beginning to form. People can, they're more of a hunter-gatherer society rather than just, straight trying to survive. And so they start asking questions of what is this stuff that we're surrounded with, right? What actually is it? Well, the Greeks believed that matter was composed of earth, water, air, and fire. And there was a fifth one they called aether, which was actually kind of the substance of the gods. But really the four on earth were earth, water, air, and fire, and that everything was one of those four substances. So all the solid was earth, made out of one substance called earth. Every liquid was called water, some kind, air, right, the stuff that we move through, and fire. And the other part that they believed here was that it was infinitely divisible into smaller pieces. Okay, that you could keep cutting it in half, cut it in half, cut it in half, cut it in half, and there would always be a piece left. Okay, that you wouldn't get down to a unit that was divisible or indivisible. Okay, so that you could just keep cutting it on and on and on. The first one to suggest otherwise was a guy named Democritus, the Greek philosopher. Okay, 460 to 370 BC. He's a philosopher who first proposed the idea that matter was not infinitely divisible. Okay, now that he had no science to this, right? He's not a scientist. He doesn't have machines to help him figure this out. This is entirely just theorizing. He says, well, if I have some sort of substance and I cut it in half, and then I cut it in half again, and I keep cutting it in half over and over and over, eventually I'm going to arrive at a point that the object I'm trying to cut is going to be too thin for the scissors or knife or whatever it is that I am trying to cut it with, that there's got to be some point where there's actually a unit that is indivisible if we just keep cutting this thing down. And so he called that unit atomos, okay, so made of indivisible atomos that could not be created, destroyed, or divided. All right? And this is where we get the word atoms from. It means indivisible, okay, in Greek. Now, again, not a scientist, just entirely based off of logic that if we keep cutting something in half, eventually we can't cut it anymore. We will reach a final unit. Well, you might be able to guess that we don't really talk a whole lot about Democritus in, history class. So he didn't really get very famous, and the reason being is not too long after he suggests that a much more famous Greek philosopher, Aristotle, right? So he's 384 to 322 BC. He rejects this idea of atoms. Okay, he believes atoms could not that he did not believe atoms could move through empty space. So that it didn't exist. Atoms didn't exist. So he thought everything was just one solid substance all the way through. And so he rejects Democritus's suggestions. And, well, Aristotle's a lot more famous. People are going to believe this, okay? They're just going to trust Aristotle on this. And if you notice, we don't really get any development in the chemistry world for about 2,000 years, okay? That is a long time. So when he rejects Democritus's suggestion, then this is what became like the belief, right, that everyone had. It's not until the 1700s with John Dalton and early 1800s, really 1802, 1803, that he's working with chemicals. John Dalton, so an English guy, 2,000 years later. He's an English school teacher, but he's kind of like your backyard scientist, right? So he'd be, if he were alive today, he'd probably be the YouTube personality that's doing experiments in his backyard. But he's an English school teacher. And he was messing around with chemicals in his backyard, and what he was finding was that there were mass ratios in compounds. So, for instance, like water was certain percentage hydrogen and a certain percentage oxygen. Okay, he could figure that out. And it's about this time that we start, discovering elements around us. Hydrogen, oxygen, iron, okay, lead, all that sort of stuff. The common elements are starting to be found around this time. So the Aristotelian idea that empty space didn't exist is going to go away very soon, and it's thanks to John Dalton. So 1803, John Dalton proposes his atomic theory, okay, and all these points down here I would make sure these are in your notes. Make sure you got them highlighted, boxed, starred, whatever. Screenshot this now. Okay, so this is 1803, so a little over 200 years ago. So chemistry as a science really isn't that old. Okay, so what did he say? All right, and some of this is still true. Some of this we had to kind of give some correction to. But we'll just, for what it was in 1803, he was remarkably close to being correct. It says that matter is composed of extremely small particles called atoms. Okay, so we still believe that's correct, right? Atoms are indivisible and indestructible. There's some, not truth to this anymore, right? We've got atomic bombs, we've got pieces of atoms, but he is on the right track. He finally realized we've arrived at a point where we can't cut something down anymore. We call it an atom. Atoms of a given element are identical in size, mass, and chemical properties. Well, they are identical in chemical properties. They're not necessarily identical in mass or size necessarily, though size is usually a little bit easier to deal with. Mass, not necessarily. But hey, he's doing pretty good so far for being over 200 years old. Atoms of a specific element are different from those of another element. So oxygen is different than hydrogen. They're not going to behave the same way. Different atoms combine in simple whole number ratios to form compounds. Okay, both of these points still true. Okay, in a chemical reaction, atoms are separated, combined, or rearranged. Also true. So, for being 200 years old, he only missed a couple of things, and those couple of things require some really extreme situations to do. But these points here, these 6 points, make sure you know them. Okay, matter is composed of extremely small particles called atoms. Atoms are indivisible and indestructible. Atoms of a given element are identical in size, mass, and chemical properties. Atoms of a specific element are different from those of another element. Different atoms combine in simple whole number ratios to form compounds. In a chemical reaction, atoms are separated, combined, or rearranged. Dalton's work led to the law of conservation of mass. Okay, and this says that mass is conserved in any process such as a chemical reaction. So conserved meaning, in this case, not created or destroyed. Okay, that we save it. Okay, whatever we start with is what we end with. The weight that we start with, the mass that we start with, has to be the mass that we end with. In chemical reactions, mass is conserved via separation, combination, or rearrangement. Okay, Dalton's work led to the acceptance of this law. So here you've got, 4 of element A, 4 atoms of element A, plus, let's see, we got 8 atoms of element B. They combine, okay, in a 2-to-1 purple to yellow ratio into these 4 compounds. Okay, one type of compound, but 4 different parts of that compound. Okay. We didn't lose any purple pieces. We didn't gain any yellow pieces. Didn't gain any purple pieces. If we didn't have a perfect 2-to-1 ratio, say there's one extra purple one here, okay? If that's the case, let me draw one in just for the sake of drawing one in. All right, if I've got one extra purple one here, all right, I would also have one extra purple one over here. It just didn't have any yellow left to react with. Okay, that's why it would still be left over there. Okay, but the mass that we start with has to equal the mass that we end with. All right, that's what you're going to hear over and over with the law of conservation of mass. The mass that you start with, okay, has to equal the mass that you end with. Okay, so grams at the start has to equal grams at the end. So I got one example to talk through, and then one example I want you to try on your own. So this example says 16.00 grams of oxygen gas reacts with some quantity of hydrogen to produce 18.02 grams of water vapor. What was the mass of hydrogen? So remember, we said the mass that you start with has to equal the mass that you end with. So what we need to do is come up with, or what are we starting with here, and what are we ending with? Well, we're starting with oxygen, so it reacts with some amount of hydrogen. So this is what we're starting with, okay? And I would always, until you've got this down, I would make a list of what's at the beginning and what's at the end. Oxygen and hydrogen, what we're starting with, we're ending with water. Okay, so that means that the mass of these two things has to equal the mass of this one. So that means the mass of oxygen plus the mass of hydrogen has to equal the mass of water. We have the mass of oxygen, 16.00. We have the mass of water, 18.02. Use algebra, subtract 16 from both sides, and we get the mass of hydrogen is 2.02 grams. Don't forget significant figures. It's addition, subtraction. So whichever one goes the least far to the right is the least far to the right you can go in your answer. They both go to the hundredths place, so your answer goes to the hundredths place. That's why it's 2.02. Okay, I want you to read this one down here and try it on your own. See how you do.